Welcome to our lecture on the life cycle of Ascaris lumbricoides. Today, we are going to explore the fascinating and, admittedly, slightly gross biological journey of the human roundworm. This microscopic stowaway can travel through your entire body, causing significant health issues along the way. By the end of this session, you will understand exactly how this parasite survives, reproduces, and spreads, which is the first crucial step in learning how to stop it. Let us begin by imagining a tiny, invisible stowaway hiding on a piece of unwashed fruit or in contaminated drinking water. When you consume this stowaway, you might think it simply goes to your stomach and stays there. However, it actually goes on a massive, multi-stop road trip through your entire body. It travels through your bloodstream, visits your liver, takes a vacation in your lungs, and eventually makes its way back to your intestines. Understanding why it takes this complex journey is key to understanding parasitic survival. Now that we have a general idea of its journey, let us formally define our subject. Ascaris lumbricoides is a large parasitic nematode, commonly known as the human roundworm. It is the culprit behind a widespread intestinal disease called ascariasis. Biologically, it is classified as a monogenetic parasite. This means that its entire life cycle, from egg to adult, is completed within a single host species. In this specific case, that host is a human being. It does not need an intermediate animal host to develop and spread. Knowing that humans are the sole host, let us look at how the infection actually begins. The life cycle officially kicks off when a human accidentally ingests embryonated infective eggs. These eggs are typically found in contaminated soil, food, or water. Once they reach the warm environment of the small intestine, the eggs hatch into microscopic larvae. But they do not stay in the gut. Instead, these newly hatched larvae actively penetrate the intestinal wall, breaking through the tissue to enter the host's bloodstream, ready to begin their migration. Once they have entered the bloodstream, these larvae do not just wander randomly. They undergo a mandatory migration phase. This journey takes them through the liver, into the heart, and finally to the lungs. This lung phase is absolutely critical because the larvae need this specific environment to mature further. After spending some time developing in the lung tissue, they physically break into the tiny air sacs known as alveoli. This tissue damage is a key part of their development and leads to the next bizarre step in their life cycle. After breaking into the alveoli, the larvae are ready for their final destination. They literally crawl up the respiratory tract, moving from the lungs all the way up to the throat. This movement often irritates the throat, causing the host to cough and then swallow. By being swallowed, the larvae travel back down the esophagus and return to the small intestine. Here, they finally settle down and grow into massive adult worms, which can reach up to 30 centimeters in length, ready to reproduce and start the cycle all over again. Let us consolidate everything we just discussed by looking at this diagram of the life cycle. Starting at the bottom left, you can see the embryonated eggs in the soil being ingested through the mouth. Follow the arrows down to the small intestine where the eggs hatch. The red arrows represent the bloodstream migration, taking the larvae through the liver, heart, and up into the lungs. Notice how the pathway then moves up the trachea to the throat, only to loop back down into the digestive tract. Finally, In the small intestine, the adult worms reside and produce new eggs, which exit the body to contaminate the soil once more. Now that we have visualized the life cycle, we must understand why this matters in the real world. Ascariasis is one of the most common human parasitic infections, affecting over 1 billion people globally, especially in tropical areas lacking proper sanitation. Understanding this biological pathway is crucial for doctors and epidemiologists. For instance, knowing about the lung migration phase explains why infected patients often present with severe respiratory symptoms, like coughing and wheezing, long before any intestinal issues arise. Furthermore, because the eggs require warm, moist soil to become effective, public health officials can design targeted sanitation programs to effectively break the transmission cycle. To truly grasp the massive reproductive scale of this parasite, we can model its egg production mathematically. This simple linear equation helps epidemiologists predict the potential spread of the disease. The formula is E equals R times T. Here, E represents the total number of eggs produced by the female worm over a given time. The symbol R stands for the daily reproductive rate, which is an astonishing 200,000 eggs per day for a healthy adult female. Finally, the variable T represents the time in days that the worm is actively reproducing. If the time T increases, the total eggs, E, increases proportionally, leading to massive environmental contamination. If treatment kills the worm, T becomes 0 and egg production stops. Let us apply this formula to a concrete example. Imagine a patient infected with a single adult female worm living in an area without modern plumbing. We want to find out how many eggs will be released into the environment over a 30-day month. We are given the daily rate, R, as 200,000 eggs per day, and the time period, T, as 30 days. We choose our linear reproductive formula because the egg-laying rate is constant. By substituting our values, we multiply 200,000 by 30. The final answer is 6 million eggs. This physically means that in just 1 month, a single worm can contaminate the environment with 6 million eggs, highlighting the severe risk in areas lacking proper sanitation. So, we have seen that millions of eggs are produced, which brings us to an important question. How long do they survive outside the body? Ascaris eggs are incredibly resilient, but they are not invincible. They do eventually die off in the environment due to harsh conditions like ultraviolet exposure from the sun and desiccation, or drying out. Because they die off at a rate proportional to their current number, the population of viable eggs decays exponentially over time. Understanding this exponential decay perfectly models how environmental hazards slowly chip away at the parasite's survival chances in the soil. To quantify this environmental survival, we use the standard exponential decay formula. The equation is N of T equals N naught times E raised to the power of negative K times T. Let us break down these symbols. N of T is the number of viable eggs remaining after a certain time. N naught is the initial number of eggs deposited into the soil. The symbol K is the decay constant, which represents the daily rate at which the eggs die off due to the environment. Finally, T is the time elapsed in days. The negative sign in the exponent is crucial because it physically represents that the population is decreasing over time. If the decay constant K increases, perhaps due to hotter weather, the eggs die off much faster. Let us see this decay in action with an example. Suppose our batch of 6 million eggs is deposited in the soil. The decay constant K is 0.02 per day, And we want to find how many eggs remain viable after 50 days. We use our exponential decay formula because the death rate is proportional to the population. Substituting our values, we get 6 million times e raised to the power of negative 0.02 times 50. Multiplying the exponent terms gives us negative 1. The mathematical constant e raised to the power of negative 1 is approximately 0.3678, meaning about 36.8% survive. Multiplying this by 6 million gives a final answer of approximately 2,206,800 viable eggs. This physically means that even after nearly 2 months, over 2 million eggs are still capable of infecting a new host. We have covered a lot of ground today, so let us review the key takeaways. First, we learned that Ascaris lumbricoides completes a highly complex and destructive migration pathway through the human body, specifically targeting the lungs before settling in the gut. Second, we saw mathematically that a single female worm can produce millions of eggs, leading to massive environmental contamination. Third, we calculated that these eggs are incredibly resilient, surviving exponentially in harsh environments for months. Finally, all of this biology and math points to one crucial public health lesson. Breaking the cycle through proper sanitation and hygiene is our ultimate weapon against this resilient parasite. Great job following along with this complex biological journey.